Hello everyone, welcome to our lecture video. In this lecture video, we are going to calculate deflection and slope of the beam by using conjugate beam method. In the previous video, we have already explained how we can calculate the deflection and slope of the beam by using Michaelis method. So in this method, we are going to talk about how we can calculate the deflection and slope of the beam by using conjugate beam method. So firstly, let us talk about the word conjugate. Here the word conjugate simply means imaginary beam. So what we're going to do in conjugate beam method is we're going to replace our original beam. So let's say we have a simply supported beam acting over a span of length L. So in conjugate beam method, what we're going to simply is our real beam. So in conjugate beam method, this real beam is going to be replaced by our another conjugate beam, and from this conjugate beam we are going to calculate our slope and deflection for our real beam. So let me act a load W. We have a point load W acting in the middle. So in order to draw our conjugate beam, first we have some certain rules. So let's say we have our real beam, and for our conjugate beam, so this is our real beam. So if we have a fixed support, in a real beam, it is going to be free end. It is going to be free in conjugate beam, and vice versa. If there is a real if there is free in at real beam, then we are going to have fixed support at our conjugate or in our imaginary beam. So this might be a little bit confusing at first, but once we move on to our example, this is going to be clear. And if we have a roller support at the real beam, we are going to have hinge support in conjugate beam, and if we have hinge support in real beam, then we are going to have
While for our intermediate
support, it is going to be intermediate only. It is going to be intermediate support only in our conjugate beam. So now for our important part, if we have to calculate slope and if we have to calculate deflection, so this is going to be our main theme. So if we have to calculate slope of our real beam, then we are going to calculate the shear force of our conjugate beam, and if we have to calculate the deflection of our real beam, then we are going to calculate the bending moment of the conjugate beam. So this is the basic rule of conjugate beam method. So after knowing this, let me move on to my conjugate beam. So another important point, now the second important, so our first important point, so we need to understand this, while my second important point is we need to draw firstly our M by EI diagram. So our M by EI diagram will act as a load. M by EI diagram will act as load for our conjugate beam. So let me explain what does this mean, act as load for our conjugate beam. So right now I have shown my conjugate beam over here. So what we're going to do is, as I explained in my rule number 1, our hinge support is going to be replaced by roller support, while our roller support is going to be replaced by hinge support in our conjugate beam. Next is, firstly let me we have to draw our M by EI diagram. So according to my rule 2, in our conjugate beam, M by EI diagram acts as load. So what is M by EI diagram? So we know M diagram simply means our bending moment diagram. Simply that bending moment diagram is divided by our constant EI, which is our constant. EI means our flexural rigidity, E is Young's modulus velocity, and I is our moment of inertia. This is our flexural rigidity. So let me firstly draw my bending moment. So right now I have W. This is acting at a span of L by 2. So W into L by 2. So this is W L by 2. So let me put my point over here, and this point is W L by 2. So W L by 2. This is my bending moment diagram. Just write M diagram. If I divide this by EI, so what I'm going to simply do is I'm going to divide it by EI. Divide by EI, and this will act as load. So this is going to be simply my conjugate beam. So let me draw all of this. This was my rule 1, this was my rule 2. Let me just focus more on my conjugate beam. So as I explained before in my rule 2, firstly we replaced our hinge support by roller support, and roller support by hinge support, and then we draw our bending moment diagram. So let me explain more on the bending moment diagram. So we have a load W acting. This is acting at a distance of L by 2. So we are going to have a bending moment of W into L by 2. So simply we have our point WL by 2, and we simply join this. So this is going to be my bending moment or bending moment diagram. So as I explained in my rule 2, for our conjugate beam, our we need to draw M by EI diagram. So what we simply need to do is we need to divide this by EI. Dividing it by EI, it is simply like reducing our it is simply like reducing the scale. So this is going to act our load. So this is going to be my conjugate beam for this diagram, and if I calculate the shear force of this diagram, I'm going to get so let's say point A, this is point C, and point B. And if I need to find the deflection at A or slope at A, if I need to find the slope at A, I'm going to calculate shear force. I'm going to calculate the shear force at A, and if I need to find the deflection at A, I'm going to calculate bending moment at A. So this will be more clarified when when I will do a practical example. So as I said, WL by dividing by EI simply reduces our bending moment. It doesn't do anything else. And another important point of conjugate beam method is this method is used when we have no fixed EI all over the beam. We might have different EI along different section of the beam. In such a condition, we are going to use conjugate beam method. In our previous method of Macauliffe method, the EI which is known as our fixed rigidity must be constant throughout our beam. So let me give a practical example so it will be easier to understand. Firstly, let me draw a real beam. This is my real beam. I have a hinge support at A, I have a roller support at a D, and at a point B there is a load. There is a point load W. This is going to be B, this is going to be C, and I have a midpoint A, and this is acting at a distance of L by 3. B to C is also L by 3, and C to D is also L by 3. So what I need to do is I need to find the slope and deflection at different sections. So I need to find slope at A, slope at B. So we're going to find slope and deflection at a different part of this beam. So in our conjugate beam method, what we're going to simply do is, so it's our real beam. So as I explained before, so our first and foremost step is going to be calculating the reaction force. So we are going to have RA. So for our real beam, firstly we are going to calculate our reaction force RA RD. So we have RA plus RD equals to 2 times W. This is my equation 1. Next I'm going to calculate moment about A. So this is the simple steps. So I'm not going to explain more on this. Simply we are going to calculate our reaction force. Firstly, next we are going to calculate our moment about it. It's going to be W into L by 3 plus W into 2L by 3 equals to RD into L. On solving this, I'm going to get my value of RA as W and RD as W. So in our exam we need to show this step, but for a shortcut method, when we have a simply supported beam and there are just two support reactions, these support reactions are going to be equal to each other. So one reaction is simply going to be half of the total load applied. So you could have done it directly as RA equals to, so we have total load 2W divided by 2W. So we could have simply done this, but in our exam we need to show the process. So we can do that as check. So we have got our support reactions as WW. So firstly, as I explained before, we are going to draw our bending moment diagram. So before drawing our conjugate beam, first let us draw our bending moment diagram. So I'm going to draw my bending moment diagram directly. So this is my point A, this is my point B, this is my point C, and this is my point D. So bending moment about A is always going to be 0, and bending moment about B. So in order to calculate bending moment about B, just see the sections up to B. So we're going to see the sections up to B. So we're not going to see any section beyond B. So we're going to see the C up to B only. So in B I have W into L by 3. WL by 3, which is clockwise. So this is going to be my first reaction. W is this force acting upward, so let me draw like this. W is acting in this way, and this is my B, this is my B, and this is L by 3. So W into L by 3. Now for about C, I need to go a little bit upward. I need to go to the right up to C. So when I go up to C, I have one force W. This is acting at a distance of 2L by 3. Because when I move to C, L by 3 plus L by 3, 2L by 3, and W is acting downward at a distance of L by 3. So this is going to be W into 2L by 3 minus W into L by 3. So this is going to be 2W, which means again WL by 3. At C also is going to be WL by 3, and ultimately at D it is going to be 0. So this is going to be my, so this is my bending moment diagram. So as I explained before, in order to draw my conjugate beam, so in order to now I'm going to draw my conjugate beam. So let me write over here for my conjugate beam. So for my conjugate beam, I need my M by EI diagram. So for my conjugate diagram, what I'm going to simply do is, I have my bending moment diagram, so I simply need to divide by EI for all those points. So let me drop this part as well, so we don't need this reaction force. So I'm just speeding up. So right now up to here we haven't done anything new. This is the simple calculation of reaction bending moment, so I'm just speeding up the process. So now for my M by EI diagram, as I explained before, now we're going to draw our conjugate beam. So as I explained before, in my conjugate beam, my hinge support is going to be replaced by roller support, and roller support is going to be replaced by hinge support. So I'm going to have roller support, so I'm going to name this point as A dash in conjugate beam, and my roller support becomes hinge support. It's going to be my point D dash. It's going to be my point D dash. So now I have WL by 3. So as I divide by EI, the scale is going to get reduced. So suppose if so let's say if this was of, let's say, I'm just saying a random scale just to make it, so of 5 centimeter. If I divide by EI, it's not of 5 centimeter, but just to clarify it, I'm just giving an example. So if this was of 5 centimeter, right now dividing by EI, this will be just smaller. It might be like 2.5 to, or just smaller. So just for giving the idea that the scale gets reduced over here, nothing else happens, just the scale gets reduced. So this is going to be WL by 3EI. Move straight, then we are going to have again WL by 3EI, and just simply join it. Join it. It's going to be my point B dash, it's going to be my point C dash, and in the middle I have my point E dash. So in this way we have drawn our conjugate beam method, and this conjugate beam acts as load. As you can see here, this acts as load. Now we are going to calculate again. Now we are going to calculate our support reaction RA dash and RD dash for this beam, which is again we have the same length L by 3. B to C dash is also L by 3, and C dash is also L by 3. So as you can see here, we have drawn our conjugate beam in this way. So now we have UVL, uniformly varying load, for section A dash B dash. We have a UDL for section B dash to C dash, and for our section C dash to D dash, we have another UVL. So firstly, we are going to calculate our support reaction. So let me just write down over here. I'll be continuing this. RA dash plus RB dash, RA dash plus RA dash plus RD dash, sorry, RA dash plus RD dash equals to, so we have WL by 3EI. So let me just draw this separately. What is happening over here is, I have WL by 3EI, I have a UVL, and this is acting at a span of L by 3. So in order to convert our UVL into point load, we simply multiply it by 1 by 2 into WL by 3EI, which is my height, into base is L by 3, plus I have a UDL over here. So for this portion I have like this. This is acting at a span of L by 3. Again the magnitude is WL by 3i. It's the same magnitude, WL by 3i. So let me drop this. So this is going to be plus WL by 3EI into L by 3, plus again 1 by 2 into L by 3 into WL by 3EI. This is going to be the same for this part as well. So on solving this, I'm going to get RA dash plus RD dash equals to RA dash plus RDS equals to 2 by 9 WL square by EI. So as I explained before, for this simply supported case, the reaction is going to get halved. So simply RA dash will be equal to by 2, which means 1 by 2, which is going to be by, if I divide it by 2, if I half it, my reaction is going to be WL square by 9A. This is a simple trick, and RDS equals to WL square by 9EI. So you can simply do this, or you can calculate the moment as well. What you can do next, or what you can simply do is, so let me drop the upper portion as well. Or what you can simply do is, we can calculate the moment about this. So I'm just telling this to so I'm just telling this trick to reduce the time we take. So what we can else do is, we can take moment about A plus moment about A equals to 0, and we can calculate the moment as well, which is going to be a moment about moment about A dash equals to 0. So which is going to be so it will be simply copy this 1 by 2 into WL by 3 EI into L by 3. So as I explained, as I've already explained how this has occurred before, into, so from our shorter rays, so for our UVL, our distance is going to be 2L by 3 from shorter edge and L by 3 from longer edge. So our load is going to act in such a way. So you probably know this, so I'm just explaining it for in case. Plus again plus 1 by 2 into WL by 3 EI into L by 3 for our point load, and this will be acting at a distance of L by 3 plus L by 3 divided by 2, plus again 1 by 2 into WL by 3 EI into L by 3 into L by 3 plus L by 3 plus right now we are calculating distance from our longer edge, so our distance is going to be L by 3 divided by 3 equals to RD dash into L. So on solving this, we're going to get our value of RD dash as WL square by 9 EI only, WL square by 9 EI, which means our value of RA dash will be again WL square by 9 EI. So let me rub all this mess and let me write down all how we drew our conjugate beam, and we had found our reaction as RA dash and RDS as WL square by 9 EI and WL square by 9 EI. So as I explained before, now in order to calculate our slope and deflection, so we have to calculate slope and deflection of our real beam. So in order to calculate slope and deflection of our real beam, we need to calculate for slope we need to calculate shear force, and for deflection we need to calculate the bending moment of our conjugate beam. So let me explain this of conjugate beam. So let me explain this. So let's say if I have to find my slope at point A, of real beam. So let me just quickly draw my real beam as well. So this was my real beam. A, B, we had W over here, and we had W over here, and we had L by 3, and L by 3. So this is our real beam, and we had our point B, C, and E over here. So this is our real beam, and this is our conjugate beam, and we have to, and let's see if I have to find slope. If I have to find slope at theta A, of real beam, then it's going to be shear force at A dash. A dash means at this point. So shear force at A dash means is simply equal to WL square by 9 EI. So right now it is positive. Positive means it is going to be clockwise. So let me just rub this, and just draw my, so just draw in this way. So my deflection is going to be in this way. This is my point A, this is my point D, and this is going to be my theta A. So right now we're taking clockwise slope as positive. So this is going to be clockwise. So this means positive. Here positive means we're going to have the slope as clockwise. Next we're going to calculate slope as theta B. Theta B, this is going to be my B, this is my C. Theta B simply means shear force at B dash, and shear force at B dash is equal to WL square by 9 EI, WL square by 9 EI minus 1 by 2 into WL by 3 EI, WL by 3 I into L by 3. So it's going to be WL square by 9 EI minus WL square by 3 to the 9, 9 to the 18 EI. So it's going to be 9 to the, which means WL square by 18 EI. It's also again positive. Positive means again clockwise. So in this way we can calculate your theta B as well. Similarly for our, we can calculate your theta C, theta D respectively. So let me just calculate theta C as well. So let me just calculate theta C. So let me just rub this. Theta C. So theta C would mean theta C is simply shear force at C dash, which is going to be equal to, so in this case I can go from right to left as well. So right now I was going from left to right. So regarding my sign convention, when I'm moving from left to right, I'm going to take my upward forces as positive and downward forces as negative. But if I move from right to left, I'm going to take my downward forces as positive and upward forces as negative. So let me calculate my theta C by moving from right to left, because when I move from right to left, I have to use less amount of forces. So upward force is going to be taken as negative. So RD dash, which means minus WL square by 9 EI plus so this UVL is acting downward, so I'm calculating it's going to be 1 by 2 into WL by 3 EI. This base is L by 3, so it's going to be minus WL square by 9 EI plus WL square by 3 3 is 9, 9 to the 18 EI. So it's going to be, and this is going to be equal to minus WL square by 18 EI, minus WL square by 18 EI. So as explained before, minus means anti-clockwise. So as I move on to my C point, my deflection I'm going to calculate in, so for my point C, I'm going to get my slope in anti-clockwise direction. So this means that, and simply for my theta D, which is going to be my shear force at D dash. So right now in this case also I can either move from right to I can move from left to right, but when I move from left to right, I have to incorporate so many of these forces. But what I can simply do is I can move from right to left. So just look at this section. I have WL square by 9 EI, WL square by 9 EI acting upward, but while moving from right to left, upward force are taken as negative. So this is also going to be negative, which means we are going to again have anti-clockwise slope at D as well. So in this way we can calculate our slope. Next we are going to calculate our deflection. So now in order to calculate our deflection is simply going to be equal to bending moment of our conjugate beam. So if I have to calculate my deflection at point A of real beam, it is going to be my bending moment at point A dash of conjugate beam. So my deflection at point A and point D are 0, so I don't need to calculate it. So as you can see here, my deflection at point A and point B, my deflection at support reaction are always equal to 0. So as you can see, there is no any deflection or no particle displacement along at point A and D. So my deflection at point A and D are 0. Now in order to calculate my deflection at point B, del B equals to bending moment at B dash of my conjugate beam. So bending moment at B dash is going to be so let me draw this figure. This is going to be my point B dash. I have my UVL of magnitude WL by 3 EI, and I have my RA dash is going downward, it's my point A dash. So my bending moment at B dash is simply going to be RA dash into L by 3. This is producing clockwise moment about B, clockwise moment. So RA dash is WL square by 9 EI into L by 3 minus, so this UVL is going to produce anti-clockwise moment about B, which is going to be 1 by 2 into base is L by 3 into height is WL by 3 EI, and this is acting at a distance of L by 3 by 3, which is L by 9 from my longer range. So as you can see here, if I had to draw this figure again, so in order to convert it into point load, this UVL, in order to convert into point load, this will be acting at a distance of L by 3 from its longer edge and 2L by 3 from its shorter 2L by 3 from its 2L by 3 from its shorter edge. So definitely 1 by 2 into base into height to convert it into point load, and L by 3 means the distance. So after doing this, we are going to get our deflection at point B as well, which is going to be equal to WL cube by 9 3 27 EI minus WL cube by 3 3 9 3 3 9 3 3 9 9 to the 18 EI into L by 9. So if we solve this, we are going to get our value, so which is going to be equal to 5 by 162 WL cube by EI. Similarly, we can calculate our deflection at C. So del C is going to be equal to bending moment at C dash, which is going to be WL square by L into 9 EI into L by 3 plus L by 3, which is going to be 2L by 3. So again 1 by 2 into L by 3 into same, but this time it will be acting at a distance of L by 3. So it's going to be L by 3 plus L by 3 by 3 so it will be acting at a distance of L by 3 by 3 plus L by 3, again plus L by 3, again minus. So we have understood this. So it is right now acting at a distance of L by 3 by 3 for this, but with respect to point C dash, we need to add L by 3 one more of section over here, and section of here, and we have UDL. This UDL, we need to convert this UDL into point load as well. So in order to convert this UDL into point loads, we are going to simply multiply WL by 3 EI into L by 3, and this will be acting at a distance of, so let me just drop this portion, explain. That will be acting at a distance, and write it downward. So this will be minus WL by 3 EI into, this is acting at a distance of L by 3. This is acting over span of L by 3, and with respect to point C dash, it will be acting at a distance of L by 3 divided by 2, which means L by 6, because in order to convert my UDL, I need to simply divide the span gets halved. This is going to be L by 6 WL by 3, it's just W, it will be WL by 3 into acting at a span of L by 6 plus L by 6 plus L by 6, because this is with respect to point C dash. So if we solve this, we are going to get our deflection at del C. So I haven't solved this, you can simply solve it and you can get your required deflection at del C. So in this way, you can calculate your slope and deflection by using conjugate beam method. Hope this video was helpful, and if you have any queries, you can comment down below. And if you like our content, if you want to see more of our stops, do subscribe the channel. It will support me a lot and motivate me to upload more videos. Thank you.